Number 1. The Okinawa Trough Liquid Carbon Dioxide Lake. Picture the light of a remotely operated vehicle sweeping across the seafloor, and instead of sand, it catches a pool. The surface is flat and glassy, like a puddle of mercury, and it does not move the way water moves. You are not looking at water. You are looking at a lake of liquid carbon dioxide resting on the bottom of the sea. It sits in the Okinawa Trough, a basin that opened behind the Ryukyu Island arc as the Philippine sea plate grinds beneath Eurasia. A sister site sits far to the east at a vent called Champagne on the northwest Ifuku volcano in the Mariana Arc. Both hide the same impossible thing. Here is why it can exist at all. Bring carbon dioxide down below roughly 400 to 500 meters into cold and crushing pressure, and it stops behaving like a gas. It liquefies. And where that liquid meets the near-freezing seawater, a thin skin forms over it, a lattice of water molecules caging the carbon dioxide called a hydrate. That skin acts like a lid, holding a pool in place beneath the sediment. When the National Oceanic and Atmospheric Administration first reached the Champagne vent in 2004, they watched milky droplets of liquid carbon dioxide drift upward from the seabed, one of only a handful of such places ever found. At the Yonaguni Knoll, Japanese teams documented pooled liquid trapped under the sediment, a true subsurface lake. Just inches away, vent fluid can pour out hotter than 100 degrees Celsius, while the carbon dioxide pools sit almost at freezing. The water around it turns fiercely acidic, so acidic that scientists treat these sites as natural laboratories for the acidified oceans of the future. Life clings to the edges anyway. Specialized microbes, shrimp, and mussels ring the deadly margins, tolerating chemistry that would dissolve most animals. Japanese research vessels have mapped these vents with the robot Hyperdolphin and the crewed submersible Shinkai 6500. Now the sinister part. That hydrate lid is not permanent. If it fails, dissolved carbon dioxide can escape quickly, and a large release can suffocate and acidify the water above it. We have seen what concentrated carbon dioxide can do when it erupts from a lake. In 1986, Lake Nyos in Cameroon belched a cloud of it and killed more than 1,700 people in a single night. This matters right now because humanity is beginning to pump industrial carbon dioxide into deep formations under the seabed to fight climate change at sites like Sleipner in the North Sea. The liquid in these pools can be nearly pure carbon dioxide, unlike the faint gas dissolved through ordinary seawater, which is part of what makes them so useful and so unnerving to study. They sit at the crossroads of three sciences at once, volcanology and marine chemistry and climate, because they show in one small place the acidified, carbon-loaded ocean that a warming world is drifting toward. These natural pools are a preview of what we are trying to build, and a quiet warning about what could go wrong. Number 2, the Beaufort Gyre freshwater bomb. Freshwater does not sound dangerous, but hold that thought, because there is a reservoir of it spinning under the Arctic ice that could help stall a current the whole planet depends on. North of Alaska and Canada, the wind drives a vast clockwise whirlpool called the Beaufort Gyre. Year after year, it collects fresh water from rivers, from melting ice, and from the Pacific, and it holds onto it. The amount is staggering. More than 23,000 cubic kilometers of fresh water sit in that gyre, roughly twice the volume of every one of the North American Great Lakes combined. Since the 1990s, it has gained about 8,000 cubic kilometers of extra fresh water, an increase of around 40%. What keeps it piled up is a stubborn wind pattern called the Beaufort High, spinning the gyre like a flywheel. Because fresh water is lighter than salty water, it floats on top and domes upward, a lens roughly 1,000 kilometers across and tens of meters deep. And here's the trigger. If those winds reverse and the gyre begins to turn the other way, it can fling its stored fresh water out into the North Atlantic. That flood of light water would spread across the surface like a lid. And it could slow the sinking of dense water that powers the Atlantic Meridional, overturning circulation, the great conveyor that carries warmth toward Europe. Weaken that conveyor, and northwestern Europe cools, and weather patterns lurch worldwide. This is the mechanism behind the fear of abrupt climate change. It is not pure speculation. In the 1970s, a pulse of fresh water called the Great Salinity Anomaly spread through the North Atlantic and left a measurable mark on its circulation. Scientists at Woods Hole Oceanographic Institution have tracked the gyre for years through the Beaufort Gyre exploration project, and researcher Andrei Proshutinsky described its flywheel behavior. They watch it with gravity-measuring satellites and with instruments tethered to the ice, and they can see the freshwater building. What they cannot do is tell you exactly when it will let go. That uncertainty is the point. Declining sea ice keeps changing the delicate coupling between wind and water that stabilizes the whole system, so the flywheel that has spun steadily for years may not stay steady. The energy is stored, held back only by the wind, invisible from the surface, hidden beneath a shrinking cap of sea ice. That is why it earns the word bomb. The ocean's currents are a machine, and this is a mass of water sitting on the release lever, waiting for the weather to change its mind. Number 3. The Messinian salt giant. Beneath the Mediterranean, a familiar and sunlit sea, lies a hidden structure on the scale of a continent, and it is made almost entirely of salt. Between roughly 5.96 and 5.33 million years ago, in the interval geologists call the Messinian, the Earth's crust shifted and closed the narrow gateway to the Atlantic near Gibraltar. Cut off from its only real source of water, the Mediterranean baked under a hot sky and began to evaporate. It dried down toward vast salt flats, thousands of meters below the level of the world ocean, a deep and blistering hypersaline hell. What it left behind is almost impossible to imagine. In places, the salt layer is more than a kilometer thick, and in the deepest basins, it reaches 2 to 3 kilometers. The total volume of salt and gypsum is estimated at around 1 million cubic kilometers, one of the largest bodies of evaporate in the entire geological record. We found it by drilling. In 1970, the deep-sea drilling project sent the ship Glomar Challenger to core the seabed, and geologists Kenneth Shue and William Ryan read the story in those cores. The sheer amount of salt meant the sea could not have dried just once. It must have refilled and evaporated again and again to stack up that much. Salt does not sit still over geological time. It is buoyant and it flows, rising in domes and columns called diapirs that warp the sediments above them, create traps that hold oil and gas, and menace anyone trying to drill through them. The crisis ended in a single dramatic act. The Atlantic breached Gibraltar and refilled the basin in what is called the Zanclean Flood, a deluge that in places may have raced in over mere months, though the full refill took longer. Pulling that much salt out of the world ocean lowered global ocean salinity by around 6%, altering seawater chemistry and circulation far beyond the Mediterranean. Modern seismic surveys still image the salt as a bright, thick band beneath the seabed, and its slow movement continues to deform the seafloor and nudge the region's earthquakes today. Some of the strangest places in the modern Mediterranean, deep pools of lifeless brine like the L'Atalante and Discovery basins, exist because that ancient salt is dissolving back into the water. There's a debate that still runs through all of this over just how deep and complete the drying really was, and whether any life clung on in isolated pools of brine while the basin lay parched. Those very salt structures, buoyant and slowly rising, are the reason the region is a target for oil and gas and a genuine hazard for anyone drilling through them. Because a column of salt can behave in ways that ordinary rock never would. A continent of salt laid down when an entire sea disappeared, still shaping the world above it, and almost no one who swims in those blue waters knows it is there. Number 4. The SS Richard Montgomery. Some sinister secrets are not natural at all. Some are ours, and we leave them exactly where they lie because touching them is worse. In the Thames estuary off the town of Sheerness in Kent, 3 broken ship masts poke above the water at every tide. They belong to the SS Richard Montgomery, an American Liberty ship, one of more than 2,700 cargo vessels churned out to feed the Second World War. In August 1944, she was loaded with somewhere between 6,000 and 7,000 tons of munitions, bound for France to supply the Allied advance. She dragged her anchor, ran aground on a sandbank, and before salvage crews could empty her, the hull cracked and flooded. They got some of the cargo off. They did not get all of it. To this day, an estimated 1,400 tons of explosives remain inside the wreck, thousands of high-explosive bombs and cluster fragmentation bombs sitting in shallow water only about 2.5 kilometers from Sheerness, right beside the shipping approach to the Thames. The official judgment is blunt. Trying to remove the munitions is considered more dangerous than leaving them alone. So the wreck is watched around the clock, ringed by an exclusion zone, tracked by radar, and marked with buoys. In 1970, a report estimated that if the cargo went off, it could throw a column of water and debris as high as 3,000 meters into the air. A blast like that could raise a wave and blow out windows across Sheerness, damaging thousands of buildings in an instant. The Maritime and Coast Guard Agency and the Department for Transport keep constant watch, and regular sonar surveys track the hull as it corrodes and slowly collapses. In 2020, surveyors studied whether the mast should be cut down, worried that if they fell into the wreck, they might disturb what lies below. The stakes have only risen with the growth of the nearby London Gateway port and a proposed liquefied natural gas terminal on the Isle of Grain. The explosives are degrading, yes, but underwater, compounds like the ones packed into those bombs can stay viable for decades, and many still are. So it waits, a genuine wartime bomb the size of a ship, resting a short walk from a living town. The uncertainty is what makes it so uneasy, because no one can promise exactly how those decaying shells will behave, and the safest verdict the experts can offer is that leaving them still is less dangerous than the alternative. So the country has chosen to live beside a bomb rather than risk setting it off, watching it corrode a little more each year, its mass breaking the surface like markers on a grave that no one dares to open. Number 5. The Storegga Slide. The last secret was a bomb we made. This one is a bomb the seabed set off by itself, and it rewrote the map of Europe. Off the middle of the Norwegian coast lies the scar of one of the largest submarine landslides ever discovered, the Storegga Slide. The best studied collapse happened about 8,150 years ago. In a single geological instant, roughly 3,000 cubic kilometers of sediment tore loose from the edge of the continental shelf and roared down into the deep. The affected area covers around 290,000 square kilometers, and the debris ran out for hundreds of kilometers across the Norwegian Sea. A slide that size shoves the water above it, and the water answered with a tsunami. It swept the coasts of Norway, of Scotland, of the Faroe Islands. In Shetland, geologists find the sand it left stranded 20 to 30 meters above where the sea stood at the time. In Scotland, that same tsunami layer is preserved in coastal sediments around places like Montrose, and the timing carries a human weight because this wave struck as Doggerland was drowning. Doggerland was the low, rich land bridge that once joined Britain to mainland Europe, already shrinking under rising seas at the end of the Ice Age. The Storegga tsunami may have delivered a devastating final blow to the people still living there. What set the slope off is still debated. A leading idea points to methane hydrates in the sediment breaking down and weakening the slope, combined with the heavy load of material dumped there by melting glaciers. Another points to earthquakes as the crust rebounded after the ice's weight lifted away. The slide zone is not some empty corner of the map either. It now holds the Ormen Lange gas field, and before that field could be developed, engineers had to study Storegga carefully to judge the risk of another collapse tearing through their pipelines. The scar has been mapped in detail, and the record shows the slope has failed more than once over hundreds of thousands of years. That is the uneasy modern question. As the oceans warm and hydrates grow less stable, could such a slope be primed to move again? Along some North Sea coasts, the waves may have reached 3 to 6 meters, and higher still, where they funneled into narrow inlets, enough to obliterate any low-lying settlement in their path. The proof is already written in the sand of 100 coastlines. The floor of the sea can collapse, and when it does, it can erase a country overnight. Number 6. The Ontong Java Plateau. Now the scale jumps again from a landslide to the single largest volcanic thing hidden anywhere beneath the sea. Northeast of the Solomon Islands, under the southwest Pacific, sits the Ontong Java Plateau, the biggest known large igneous province on Earth. It covers roughly 2 million square kilometers, an area comparable to Alaska or to much of Western Europe. It formed around 120 to 125 million years ago in the early Cretaceous, and it represents somewhere between 50 and 100 million cubic kilometers of erupted basalt. Its crust is monstrously thick, more than 30 kilometers in places, when ordinary ocean crust is only about 7. The leading explanation is a mantle plume, a colossal upwelling of hot rock whose bulbous head reached the surface and flooded the seabed with lava. A minority of researchers have even proposed that an asteroid impact triggered it, though the evidence for that is thin. Whatever lit the fuse, the eruption would have breathed enormous volumes of carbon dioxide and other gases into the ocean and the air. And its birth lines up in time with a global crisis called Ocean Anoxic Event 1A, the Selly event, when large parts of the sea lost their oxygen. Those anoxic events killed marine life and buried black carbon-rich shale across the world. Scientists have drilled into the plateau on ocean drilling program expeditions to sample its basalts and read its history. The plateau is so buoyant and so thick that it refuses to be swallowed back into the earth. Instead of subducting, it is jammed against the Solomon Islands arc and even reversed the direction of subduction there, a rare tectonic event. Because it never sank, it preserves a record of ancient super eruptions that most ocean crust would have destroyed long ago. Researchers such as Mike Coffin helped to define both this plateau and the whole concept of large igneous provinces, and there is evidence it was once part of an even greater volcanic mass, joined to the Manihiki and Hikurangi plateaus before the plates rifted them apart. It is easy to think of the ocean floor as passive and dead. The Ontong Java Plateau is the opposite. To put its scale in modern terms, a single event laid down enough rock to bury a landmass the size of Alaska under kilometers of basalt, and it did so while the dinosaurs still walked the continents above. It is the buried monument to an eruption so vast it may have helped strangle the seas of its age, and it is still hiding, mostly unmapped, beneath the blue. Number 7. The Monterey Canyon. Not every dark corner is far away. One of the most dramatic hides just off a crowded California coast, and it is on the move. In Monterey Bay lies the Monterey Canyon, one of the deepest submarine canyons on the entire Pacific coast of North America. It plunges to more than 3,600 meters and stretches roughly 470 kilometers out to sea, rivaling the Grand Canyon in both depth and the steepness of its walls. The strangest part is how close it starts. The head of the canyon begins near Moss Landing, only a few hundred meters from the beach, so the abyss opens almost at the shoreline. Its origin is debated because it is far older than the small rivers that feed the bay today. Since 1987, the Monterey Bay Aquarium Research Institute has studied it more closely than almost any deep place on Earth. Between 2015 and 2017, in the Coordinated Canyon Experiment, they wired the canyon floor with instruments to catch it in the act. What they caught was violence. Turbidity currents, underwater avalanches of sediment, raced down the canyon at speeds measured up to around 8 meters per second. These flows are strong enough to pick up heavy instrument frames and drag them hundreds of meters, burying some of the gear entirely. They also carry sand and organic carbon from the coast down into the deep, part of how the planet moves carbon into the abyss. The canyon is alive with more than sediment. Near the neighboring Davidson Seamount, researchers found the octopus garden, where thousands of octopuses gather to brood, and cold seeps feed methane-based communities along the system. All that movement is a hazard too, capable of threatening the undersea cables that carry the world's data. At its far end, the canyon feeds the Monterey Fan, a great spreading pile of sediment on the abyssal plain. Scientists like Charles Paul have used its accessibility to reconstruct how these avalanches behave, triggered by storms, by floods, and possibly by earthquakes. That accessibility is exactly why it matters. Most of the deep sea is a long, expensive journey away. This Grand Canyon of the Pacific sits within reach of a research pier, quietly reshaping itself beside one of the most watched coastlines in the world, a reminder that the darkest corners can be almost close enough to touch. And the reach of these flows is not just local, because as they carry organic carbon from the shallows down into the deep sea, they quietly become part of the planet's carbon cycle, one more thread linking a canyon off California to the chemistry of the whole ocean. Number 8. The Gulf of Mexico. Dead Zone. Some sinister secrets we build on purpose without ever meaning to, and this one comes back every single summer. Off the coast of Louisiana and Texas, a huge region of water near the seafloor loses almost all of its oxygen. Scientists call it hypoxia, and they draw the line at 2 milligrams of oxygen per liter, below which most marine animals cannot survive. The zone forms where the Mississippi and Atchafalaya rivers pour out into the Gulf, carrying a heavy load of nitrogen and phosphorus from fertilizer, from sewage, and from runoff across the land. Those nutrients feed explosive blooms of algae. The algae die, sink, and rot, and the bacteria that decompose them strip the oxygen out of the bottom water. Meanwhile, a layer of fresher, warmer water sits on top like a lid, a process called stratification, so no new oxygen can mix down. In recent years, the dead zone has averaged around 15,000 square kilometers. In 2017, it hit a record of about 22,700 square kilometers, roughly the size of New Jersey. Every summer, teams from the National Oceanic and Atmospheric Administration and from the Louisiana University's Marine Consortium go out to map it, work built on the long-term monitoring begun by scientist Nancy Rabelais back in the 1980s. On the bottom, the animals that cannot run, the clams and the worms, simply suffocate while fish and shrimp flee, tearing holes in the fishery. The root of it reaches deep into the continent because the Mississippi drains about 41% of the mainland United States, so fertilizer from farms across the Midwest ends up choking the Gulf floor. A federal task force set a goal of shrinking the zone to about 5,000 square kilometers, a target that has been missed again and again. Flood years like 2011 make it worse by flushing even more nutrients downstream, and a warming climate may intensify both the rainfall and the stratification that lock the oxygen out. This is not unique to the Gulf. More than 400 dead zones have been documented around the world, from the Baltic Sea to Chesapeake Bay. But the Gulf's is one of the largest, a suffocating state-sized wasteland that materializes on the seabed year after year, almost entirely out of public sight, made by choices happening 1,000 miles inland. The damage is not only ecological but economic, because the shrimp and fish that flee the low oxygen water scramble the catch that coastal communities depend on, turning a chemistry problem far offshore into a livelihood problem on the docks. Number 9. The SS El Faro. The deep does not only keep ancient secrets, it still swallows modern ships whole, and sometimes it keeps their final words. The SS El Faro was an American cargo ship, a roll-on roll-off vessel built in 1975. On October 1st, 2015, she sailed straight into Hurricane Joaquin near the Bahamas and went down with all 33 people aboard, the deadliest American commercial maritime disaster in decades. She was running a routine route from Jacksonville, Florida to San Juan, Puerto Rico. Her captain, Michael Davidson, chose a track that carried the ship close to a hurricane that was strengthening faster than the forecasts he was reading. As the vessel listed, she lost lubricating oil pressure and then lost propulsion, leaving her powerless in the heart of the storm. She sank in about 4,600 meters of water, roughly 15,000 feet down. Finding her was its own extraordinary effort. A search led by the Navy and the National Transportation Safety Board, using the research vessel Atlantis with deep-tow sonar and a robot, located the wreck on the abyssal seafloor. Then they went back for the black box. Recovering the voyage data recorder from 4,600 meters in 2016 was one of the deepest such recoveries ever attempted. What it held was harrowing. 26 hours of bridge audio, the voices of the crew growing more alarmed as the sea rose around them. The National Transportation Safety Board and the Coast Guard pulled the disaster apart. They pointed to the captain's decisions, to weather information that lagged the real storm, and to flooding through an opening in the hull. The forecasts he trusted simply could not keep up with how fast Joaquin intensified. Out of the wreckage came recommendations on weather routing, on ship stability, and on survival gear, along with hard criticism of older designs with open lifeboats that stood no chance in seas like that. The transcript of those final hours became a public document, a raw and haunting record of a tragedy that better information might have prevented. El Faro is the modern proof that for all our satellites and safety rules, the ocean can still take a ship and everyone on it, drop them 3 miles down into the dark, and hold their last conversation there until we are willing to go and listen. The investigators found that so much of the tragedy came down to information, forecasts, and routing advice that could not keep pace with a storm intensifying by the hour, which is why the recommendations that followed reach beyond one ship, into how every vessel reads and trusts the weather, closing in around it. Number 10. The USS Arizona's Black Tears. The last secret is the most human of all, and it has been weeping for more than 80 years. The USS Arizona was a battleship sunk during the Japanese attack on Pearl Harbor on December 7, 1941. A bomb reached her forward ammunition magazines, and the explosion tore the ship apart and sent her to the bottom in minutes. 1,177 of her crew died, the greatest loss of life on any warship in American history. She rests in the shallow water of the harbor still, and a white memorial now spans her hull. When she was hit, she carried around 1.5 million gallons of fuel oil. More than 8 decades later, that oil has never stopped coming up. Every day, the wreck releases something like 2 to 9 quarts of it, and the droplets rise and spread into shimmering rainbow films across the surface above the memorial. People call them the black tears, the tears of the Arizona. An estimated 500,000 gallons of oil may still be trapped inside of the corroding hull. The National Park Service manages the memorial and watches that slow release, caught in a hard question. Do you leave the oil where it is, or do you try to remove it? The wreck is not just a hazard, it is a grave. More than 900 sailors remain entombed within her, so any disturbance is a matter of deep respect as much as engineering. And the clock is running, because corrosion is thinning the steel, as microbes and electrochemistry slowly eat the metal away. Researchers from the Park Service and from universities have modeled how long the hull can hold, measuring corrosion rates and remaining thickness and the microbes at work, and some estimates suggest the structure could begin to fail within decades, which might release the oil far faster than the gentle daily seep we see now. For the moment, it remains a slow threat to the harbor's ecosystem, monitored and understood. But it is also something harder to measure, and so the same corrosion that could one day release the oil is also slowly dissolving the tomb itself, which is why every study of the wreck is really 2 questions at once, an environmental one about 500,000 gallons of fuel, and a human one about how long a grave can be allowed to stand before we must decide whether to intervene. A sunken ship, full of the men who died in her, still bleeding oil into the light. A decades-long countdown resting quietly beneath a place where millions come to remember the dead. Step back from the 10, and a pattern surfaces. The deep sea does not hide things because it is empty. It hides them because it is almost impossible to reach. Pressure and darkness act as a natural vault, sealing away whatever falls or forms below. And in that vault, chemistry does things that would be impossible at the surface. Carbon dioxide becomes a liquid lake. Water grows so salty and starved of oxygen that it turns into a lifeless pool. Fresh water piles into a dome held up by nothing but wind. The sea also works as a time capsule, keeping a continent of Messinian salt, an ancient Cretaceous plateau, and the scar of a landslide older than most human history. Alongside these natural secrets sit the ones we made, a wartime wreck full of live bombs, a dead zone fed by farms 1,000 miles away, a battleship still leaking its fuel. What ties them together is scale that defeats the imagination. We reach for the Great Lakes for the size of a state, for the area of a continent, because the raw numbers slide off the mind, and nearly every one of them shares a single quiet danger. It is invisible from the surface. New tools are only now pulling them into the light. Robots and submersibles, satellites that weigh the ocean by its gravity, seismic surveys that see through the seabed. Look closely, and the same motif keeps returning, a cap that could fail. A hydrate lid over the carbon dioxide, a wind holding back the freshwater flood. A corroding hull over 500,000 gallons of oil. A layer of warm water sealing the oxygen away. Notice, too, how these secrets cluster in the same kinds of places, in trenches and back arc basins, and along the steep margins where continents drop away. Because those are the zones where the earth is most active, and the water is deepest and least watched. Some of them are slow, unfolding across millions of years like the salt giant or the plateau, and some are fast, a landslide or an explosion that happens in minutes, and the sea keeps both kinds side by side with the same indifference. The deep is an archive of both the planet's story and our own, and the question that runs beneath all 10 is simple and unsettling. How much of it can we actually see coming? The honest answer is not enough. We have directly observed only a small fraction of the seafloor, and every deep dive is slow and expensive. A robot or a submersible lowered painstakingly into the dark. That leaves enormous gaps in our watch over slow-moving hazards, the kind that give no warning until they arrive. We cannot say when the Beaufort Gyre will let go, when a slope like Storegga might fail again, or when the hull of the Arizona will finally give way. Worse, our attention is biased toward what is easy to reach. Monterey Canyon is studied so intensely partly because it opens almost at the beach, while countless remote basins go unwatched. And the deep punishes the instruments we do send. The turbidity currents in that very canyon rip heavy frames from their moorings and bury them. Sometimes the data itself arrives too late, as it did for the El Faro, whose forecasts lagged the storm that killed her. There is an ethical limit too. Some of these places are graves as much as hazards, so we deliberately leave the Richard Montgomery and the Arizona largely undisturbed, choosing to watch rather than to touch. Long-running programs carry most of the load, the institutes at Monterey and Woods Hole, the Marine Consortium mapping the Gulf every summer. New tools are arriving, autonomous vehicles that roam without a tether, satellites that track water by its gravity, sensors seeded across the seabed. Consider how much rides on the long-term programs that most people never hear about. The Institute at Monterey that has watched its canyon since 1987. The scientists at Woods Hole tracking the Beaufort Gyre with satellites and ice-tethered instruments. The Marine Consortium that goes out every summer to map the Gulf Dead Zone from scratch. Without those unglamorous year-after-year measurements, we would not even know these hazards were changing, let alone how fast. That is the quiet cost of a hidden world, that simply keeping our eyes on it takes decades of patience and funding, and the moment we look away, the record goes dark. But for now, the unknowns still outnumber the knowns by a wide margin, and a warming ocean is quietly rewriting the rules on all of it. Follow that warming, and several of these secrets start to connect. Rising ocean temperatures can destabilize the very methane hydrates blamed for helping trigger the Storegga Slide, which is why a warmer sea raises the specter of new submarine landslides and the tsunamis they spawn. Warming also drives the freshwater story of the Beaufort Gyre and the fear of a weakened Atlantic conveyor. It intensifies the stratification and the rainfall that swell the Gulf of Mexico dead zone. It pushes the whole ocean toward the acidity that the carbon dioxide vents in the Okinawa Trough preview in miniature, even as we begin storing our own carbon beneath the seabed and hope those caps hold. And the deep past speaks to the future here, because the Ontong Java Plateau is tied to an ancient event when the oceans lost their oxygen, a natural experiment in what floods of volcanic carbon can do to a sea. These threads feed back on one another in ways that are genuinely hard to model, which is why the uncertainty ranges are so wide and why they matter so much. Better monitoring would narrow them, but the deeper levers sit upstream in the fertilizer spread on distant fields and the carbon poured into the air. The unsettling lesson of the Ontong Java Plateau is that this has happened before, that a flood of carbon into the ocean once helped drive it into an oxygen-starved crisis that killed off marine life and left black shale across the world, and that the sea recorded the whole thing for us to read. What makes the modern versions so hard to pin down is that they feed on one another, a warmer surface locking oxygen away here, a freshwater pulse slowing a current there, each change nudging the next in loops that resist a clean prediction. That is exactly why the wide bands of uncertainty in the models are not an excuse to relax, but a reason to watch more closely. The darkest corners of the sea are not sealed off from us after all. They are wired to the choices we make on land. If these 10 stories share a lesson, it is humility. Again and again, scale beats intuition. The mind cannot hold a lake of liquid gas, a continent of buried salt, or a landslide that drowned a country, so we underestimate them until the evidence forces the issue. A second lesson is that watching can be wiser than fixing. With the Richard Montgomery and the Arizona, the safest and most respectful path has been to monitor rather than to disturb. A third is the cost of ignoring slow hazards, the dead zone that returns each summer, the hull that thins by the year, the freshwater dome that keeps growing. The ancient catastrophes reframe the present because a slope that failed 8,000 years ago and a sea that dried 5 million years ago are not just history. They are demonstrations of what this planet is capable of. And running through all of it is the tangle of natural and human causes, a landslide triggered by nature beside a dead zone triggered by us, often demanding the same mix of curiosity and caution. There's a fourth lesson hiding in the pairings. The way a natural catastrophe like Storegga sits right beside a human one like the dead zone, and how often they call for the very same response: careful study, honest numbers, and the discipline to act before the slow problem becomes a sudden one. We tend to fear the ocean's monsters, the things with teeth. But almost every secret in this list is quieter than that: a chemistry, a pressure, a slow corrosion, a mass of water in the wrong place. The deep sea, in the end, is not only a threat, it is a teacher, patient and unsentimental, showing us the size of the forces we live beside. Return, at the end, to that first image, the beam of a robot's light falling on a flat, still pool of liquid carbon dioxide resting on the seafloor. It is beautiful and it is wrong, and it is a small window onto everything the ocean holds just out of reach. The sea is the largest unexamined space on our planet, and what it hides is natural and ancient and human all at once. A plateau older than the mammals, a salt giant older than our species, a battleship that sank within living memory. Often the word sinister just means not yet understood, a mystery waiting for a light to be shown on it. But sometimes it means something more literal, a real countdown, a cap that will one day fail, a hull that will finally give. That is the tension these darkest corners leave us with. Wonder and dread braided together, the thrill of finally seeing a place no one has seen, and the weight of knowing what we have found. So much of it still sits down there in the cold and the dark, patient, waiting. Every one of these 10 began as something no one knew: a pool, a dome, a layer, a scar, until a drill core or a robot's light or a summer survey pulled it into view. And each discovery only sharpened the outline of how much remains unseen. And the deepest truth of the deep is that for every secret we finally drag into the light, the ocean is still keeping more.